Hi guys, welcome to another lecture in the series Medicinal Chemistry 2. And today we're going to be talking about nitrates and nitrites, as well as positive inotropic agents. So off the bat, nitrites relieve angina pectoris. So most coronary artery disease conditions are caused by deposits of fat, cholesterol, just plaque in the inner lining of large and medium-sized arteries serving the heart. The process is characterized by an insidious onset of episodes of cardiac discomfort caused by ischemia from inadequate blood supply to the tissues. And so angina pectoris, or just angina for short, the principal symptom of ischemic heart disease is characterized by a severe constricting pain in the chest, often radiating from the precordium to the left shoulder and down the arm. So angina is, in short, a type of chest pain, pressure, or discomfort that happens because the heart is not receiving enough oxygen due to narrowed coronary artery. So the syndrome has been described since 1772, but it was not until 1867 that amyl nitrite was introduced for the symptomatic relief of angina pectoris. So amyl nitrite, the structure for it is seen here. So this is a nitrite, and generally speaking, nitrites relieve angina pectoris by dilating the coronary arteries, and they have more limited application in treating things like asthma, GI spasm, or certain cases of migraine headache. So we now know that the coronary blood vessels in the arteriosclerotic heart already are dilated, and that ordinary doses of dilator drugs do not significantly increase blood supply to the heart. Instead, anginal pain is relieved by a reduction of cardiac consumption of oxygen. So although vasodilators are used in the treatment of angina, a more sophisticated understanding of the hemodynamic response to these agents has broadened their clinical usefulness to other cardiovascular conditions. So because of their ability to reduce peripheral vascular resistance, vasodilators such as your organonitrates, your angiotensin converting enzyme ACE inhibitors, which we met, or angiotensin receptor blocking agents, so they are used to improve cardiac output in some patients with congestive heart failure, which is CHF for short. All right, so continuing on this discussion, the coronary circulation supplies blood to the myocardial tissues to maintain cardiac function. So it can react to the changing demands of the heart by dilating its blood vessels to provide sufficient oxygen and other nutrients and to remove metabolites. So myocardial metabolism is almost exclusively aerobic, which makes blood flow critical to the support of the metabolic processes of the heart. All right, so the principal goal in the prevention and relief of angina is to limit the oxygen requirement of the heart so that the amount of blood supplied by the stenosed arteries is adequate. And we have an image here of stenosed arteries where you have plaque as well as a clot obstructing the flow of blood here. So nitrate esters such as nitroglycerin, and we see the structure here. So this is a nitrate ester. They lower arterial blood pressure and in turn reduce the work of the left ventricle. This action is produced by the powerful vasodilating effect of the nitrates on the arterial system, and to an even greater extent on the venous system. So the result is reduced cardiac filling pressure and ventricular size. So this reduces the work required of the ventricle and decreases the oxygen requirements, allowing the coronary system to satisfy the oxygen demands of myocardial tissue and relieve, therefore, anginal pain. So the contractile activity of all types of muscle that is smooth or skeletal is regulated primarily by the reversible phosphorylation of myosin. So together with actin, myosin participates in a cascade of biochemical events that are part of the processes of muscle contraction and relaxation. So this cascade is seen here. At the end of it, well, I should say, at the start of it, we have calcium and beta agonists, right? And at the end of it, we have contraction and relaxation of the muscles. So clearly there are a series of reactions. So you have the calcium channel, the calcium enters, it forms a calcium calmodulin complex, which then combines or activates your MLK, and your MLK is your myosin light chain kinase. So it is activated, that is the star there, but by the calcium calmodulin complex, it becomes activated, and it therefore phosphorylates myosin LC, right, which is myosin light chain. It is phosphorylated, and then in the presence of actin, we have contraction. And if myosin is dephosphorylated to myosin LC in the presence of myosin phosphatase, then you have relaxation. And just to mention the beta agonist route, you have the adenylate cyclase playing a role there in the beta agonist, and we have a conversion to CAMP, and then that therefore phosphorylates MLK, and that therefore would result in relaxation of the muscles. So there are a cascade of biochemical events that plays a very important role in the processes of muscle contraction and relaxation. So it can start with calcium or a beta agonist and essentially end up being contraction, relaxation, or relaxation via this route here. So we mentioned CAMP, as the phosphorylating agent here. It's your cyclic nucleotide, and it's cyclic adenosine monophosphate, and I think we're gonna mention now cyclic guanosine monophosphate, so we're gonna call it CGMP or CAMP. They both play important roles in the regulation of smooth muscle tension as seen. So the activity of CGMP in smooth muscle relaxation is affected by the exogenous and endogenous agents, right? So it is suggested that nitrovasodilators, they undergo metabolic transformation in vascular smooth muscle cells to form nitric oxide. So as we can see here, we have our nitrovasodilators in endothelial cells releasing nitric oxide, and as a result of that, we can see where guanylate cyclase or GC is activated, and then that therefore converts GTP to cGMP, and therefore it can now phosphorylate MLK, and therefore that would result in the muscle relaxation. So nitric oxide mediates smooth muscle relaxation by activating guanylate cyclase, as I said already, to increase intracellular concentrations of cGMP. And then cGMP activates protein kinases that can regulate free calcium levels, as we saw previously, in the muscle cell and cause relaxation of the smooth muscle by phosphorylating MLK, as we see here, right? So this is how it works. This is how nitric acid causes smooth muscle relaxation. So it can happen via a endogenous agent, and it can happen via a exogenous agent, right? So this is the mechanism of action. All right, so a short-lived free radical gas, which is nitric oxide, is widely distributed in the body and plays an important role by its effect through cGMP on the smooth muscle vasculature, as we just saw. It is synthesized, so nitric oxide is synthesized in the vascular endothelial cell from the semi-essential amino acid L-arginine by NO, that's nitric oxide synthase. So here, we mentioned this schematic already, where you have nitric acid activating GC, and then, causing this conversion, and then phosphorylating MLCK, and then cause smooth muscle relaxation. And this image here shows the semi-essential amino acid L-arginine being converted to L-citrulline, right? And then producing your nitric acid in the presence of nitric acid synthase. And so this is how the body produces nitric oxide. So after oral administration, organic nitrates are metabolized rapidly by the liver, kidney, lungs, the intestinal mucosa, and vascular tissue. So organic nitrates, your nitrites, nitrosa compounds, and a variety of other nitrogen-containing substances such as sodium nitroprusside are, for the most part, cause their pharmacological effects by generating or releasing nitric oxide in situ. All right, so now I have an image of esters of nitrous and nitric acids. So we have mentioned nitroglycerin already. This is the structure. We've mentioned amyl nitrite. So there are other nitrites and nitrates, and these are the respective structures. So we can see a 4-carbon backbone as opposed to a 3-carbon backbone, etc., branching here. But essentially we can see the variety of nitrates and nitrites. So the production or release of nitric oxide may be impaired under pathophysiological circumstances associated with dysfunction of the endothelial tissue, right? So when it cannot happen naturally, In some ways, these drugs are viewed, so the drugs that produce nitric oxide are viewed as replacement agents for the endogenous nitric oxide generated by the nitric oxide synthase pathway from arginine, which we mentioned already. So a common feature of these drugs is that they release nitrogen in the form of nitric oxide and contain nitrogen in an oxidation state higher than +3, as would occur in, ammonia, your amines, these functional groups that you are familiar with and that are present in most biological nitrogen compounds. The nitrogen in nitric oxide has an oxidation state of +2, as seen here. Compounds such as nitroprusside, that's down here, nitroso, amines, and nitrothiols with oxidation states of +3 release nitric oxide non-enzymatically. So although they're so just go back to that diagram, we have various nitrites and nitrates here, and they have 3 different oxidation states. Well, only nitric oxide has +2, the others are either +3 or +5 depending on the structure. That is, the oxidation state is referring specifically to the nitrogen. Alright, so although their spontaneous liberation of nitric oxide is by an unknown mechanism, it involves only a 1 electron reduction, which may occur in exposure of these chemicals to various reducing agents in the tissue of vascular smooth muscle membranes. So organic nitrites such as amyl nitrite, and we saw the structure, react with available thiol groups to form a very unstable S-nitrosothiol, and we have a generic structure here, which rapidly decompose to nitric oxide by homolytic cleavage of their SN bond. So in mammalian smooth muscle, this will occur almost exclusively with glutathione as the most abundant thiol compound. All right, so we have another question. Demonstrate that should have been homolytic cleavage using curly arrows needed to produce nitric oxide in the structure below. So we just mentioned here that once the unstable S-nitrosothiols are formed, they rapidly decompose by a homolytic cleavage, and that is what I want you to demonstrate on this structure seen here. All right, so this is what I want you to demonstrate, the homolytic cleavage on this structure below. All right, so as we know, it's homolytic cleavage, which means that we're moving a single electron, and so we must have the fishhook arrow starting on the bond, one end of the arrow ending on the nitrogen, the other on the sulfur. And that is how we end up with our radicals seen here. All right, so continuing on that discussion, essentially just speaking about how we generate the nitric oxide. So sulfhydryl containing compounds such as cysteine, and we have an image below, react chemically with organic nitrates to form inorganic nitrites ions. And so the release of nitric oxide from an organic nitrate such as nitroglycerin appears to occur in a stepwise fashion involving non-enzymatic as well as enzymatic steps. So because nitroglycerin requires a 3 electron reduction to release nitric oxide, thiols may be involved in the process. So we can see here several sulfur bonds here required to release our nitric oxide. So it is basically proposed that it could happen via several routes. When our organic nitrates interact with cysteine, and whether it be with an enzyme or without an enzyme, we end up with our nitric oxide. So nitroglycerin may decompose non-enzymatically by interaction with various thiols, such as cysteine, as we mentioned, which may be present in tissue to form nitrous or thiol intermediate before undergoing enzymatic transformation to release NO, or nitric oxide. And so nitroglycerin also readily releases nitric oxide by acting on an enzyme system attached to the cellular surface membrane of the smooth muscle. The process may include glutathione S transferases, which convert nitroglycerin to a vasoinactive nitrite, which may then release nitric oxide non-enzymatically. All right, so we have various nitrites and nitrates, as we see here under the heading of compound in this table. So varying the chemical structure of the organic nitrates yields differences in the speed of onset, duration of action, as well as potency. Although the number of nitrate ester groups may vary from 2 to 6 or more depending on the compound, there is no direct relationship between the number of nitrate groups and the level of activity. So unfortunately, we don't have that correlation between the potency or the level of activity and the number of nitrate groups, right? So as we can see, we see some tetranitrate, dinitrate, or just one nitrate, but there is no direct relationship between the number of nitrate groups and the level of activity. So we can see here, action begins, maximum effect, and duration of action varying here. So the orientation of the groups within the molecule may affect potency. The lipophilicity of the nitrogen oxide containing compound produces a much longer response of vasodilatory action. So the highly lipophilic ester nitroglycerin permeates the cell membrane, allowing continual formation of nitric acid within the cell. So clearly we're seeing here that if the nitrate is more lipophilic, then it has a longer response to vasodilation. All right, so we have a question. Explain the statement made with reference to nitrovasodilators. I quote, "In some ways, these drugs are viewed as replacement agents for the endogenous nitric oxide generated by the nitric oxide synthase pathway from arginine." So explain what it means, or break it down, in other words. All right, so my attempt at breaking it down is this, and I'm sure your attempt will be different. But the body naturally produces nitric oxide, and that process starts with the L-arginine in the presence of the enzyme nitric oxide synthase, etc. Right? So when the need arises, drugs are needed to continue to supply the nitric oxide. So this is how I'm saying this in other words, and hopefully that further explains the statement. All right, so the first drug that we're going to look at is amyl nitrite. And we already met the structure as seen here. It's a mixture of isomeric amyl nitrites, but is principally isoamyl nitrite. It may be prepared from amyl alcohol and nitrous acid by several procedures. Usually amyl nitrite is dispensed in an ampoule form, which is a small sealed glass capsule containing a liquid, so that's an ampoule, and used by inhalation or orally in alcohol solution. Currently, it is recommended for treating cyanide poisoning, although not the best antidote. It does not require intravenous injections. So that's amyl nitrite. For nitroglycerin, it was one of the first members of this group to be introduced in medicine and remains an important member of the group. Glyceryl trinitrate is that is another way of saying nitroglycerin, is the trinitrate ester of glycerol and is listed as available in tablet form in the USP. It is prepared by carefully adding glycerin, as seen here, or glycerol, to a mixture of nitric acid and fuming sulfuric acid, and that is how so this is the structure of nitroglycerin, how it's prepared. This reaction is exothermic, and the reaction mixture must be cooled to between 10 to 20 degrees Celsius. So the ester is a colorless oil with a sweet burning taste. By transformation of the nitroglycerin to the dinitrates and the increase of intracellular cGMP precede vascular relaxation. So we have some other nitrates. So we have sodium nitrite, and that's the structure. So that's basically, and we saw some of these already. So essentially you have dinitrates, you have 4 or tetranitrates, and this is, the structure, it's arranged differently, but this is still a tetranitrate, and of course we have sodium nitrite. So we have a question here. Propose a synthesis for these nitrate esters. All right, so as we saw on the couple slides ago, in the synthesis of nitroglycerin, we started off with glycerol in the presence of a mixture of acids, whether it be nitric acid with sulfuric acid, and you end up with nitroglycerin. So it's generally an acid or acids and alcohol seen here that it results in the formation of this nitrate ester. All right, so now we're gonna speak briefly about positive inotropic agents. So these are agents that successfully increase the force of contraction of the heart and may be particularly useful in the treatment of CHF, which is congestive heart failure. So in CHF, the heart cannot maintain sufficient blood flow to various organs to provide oxygen-rich blood. So agents that increase the force of contraction allow greater amounts of blood to be distributed throughout the body, and in turn reduce the symptoms associated with congestive heart failure. So most of the positive inotropic agents exhibit their effects on the force of contraction by modifying the coupling mechanism involved in the myocardial contractile process. Now this plant, this lovely plant that you're seeing on the screen, is called Foxglove, or it's known as Digitalis, and there are various species. So this plant is important, with regards to positive inotropic agents. So Digitalis glycosides, which is a mixture of products isolated from this plant, were first used as a heart medication from way back in the 1500 BCs, when the Ebers Papyrus, the ancient Egyptians reported their success in using these products. So throughout history, these plants extracts have been used as arrow poisons, emetics, and diuretics. The dichotomy of the poisonous effects and the beneficial heart properties is still evident today. The cardiac glycosides are still used today in the treatment of CHF and atrial fibrillation, with careful attention paid in monitoring the toxicity that these agents possess. All right, so the cardiac glycosides, as we mentioned, they include two distinct classes of compounds. You have your cardinalides and you have your bufadienolides, and the structures are seen here. So the only difference between these types of compounds is the substitution at C17, which is here. So this is C17 on the steroid moiety, where the cardinalides possess an unsaturated butyrolactone here ring, whereas the bufadienolides have an alpha pyrone ring. So this is our alpha pyrone ring. So that is the difference between both classes of compounds. Pharmacologically, both have similar properties and are found in many of the same natural sources, just like from your Foxglove or Digitalis, including plant and toad species. So this remarkable fact is based quite simply on the unique ability of nature to produce extraordinarily bioactive substances which characteristically possess both a lipophilic portion in the steroidal ring. So this ring is the steroidal ring, is lipophilic, and the hydrophilic moiety in the glycosidic rings. So these are, rings in this portion, so we're not seeing when our sugar moieties, then we have glycosidic rings. So this is remarkable, as they said. The therapeutic use of these agents depends largely on a balance between the different solubility characteristics of the steroid structure and the type and number of sugar units attached to it. So this is where the sugar units are attached in the various molecules. So although the fundamental pharmacological properties reside with the steroidal nucleus, the sugars play a critical role in the biological effects elicited because they increase the water solubility of the lipid system, making them more available by translocation in the aqueous environment, and at the same time allowing transportation across fatty sites, right? So both parts of the molecule are important. So these properties uniquely balance each other and allow successful translocation to the receptive sites in the body. Ultimately, the lipophilic steroid also plays a specific role in the agent's onset and duration of action. All right, that should be no surprise. So as the steroidal rings are modified with polar groups, that is, you add on extra hydroxyls, the onset increases and the duration of action decreases. Right, so clearly you are increasing your water solubility there, so the onset will increase and then the duration of action decreases because they're easily eliminated. So the sugar residues are substituted on C3 of the steroid and are generally a glucose, various sugar molecules are attached at this position here. All right, so in terms of their mechanism of action, the cardiac glycosides elicit their effects through the inhibition of the sodium-potassium pump, right? So as we can see, or let's just go ahead with what we're saying. Inhibition of this pump increases the intracellular sodium. So this is a cardiac glycoside here, and inhibition of it causes the sodium ion concentration, intracellular sodium concentration to increase, which affects the sodium calcium exchange over here. And so this increases intracellular concentrations of calcium, which is available to activate the contractile proteins actin and myosin. So, we can go back to the previous slides where we mentioned the importance of calcium and how via series of biochemical cascades result in either contraction or relaxation of the muscle. Rings a bell? All right, so in a similar fashion, after we have the sodium increasing in intracellular concentration, that affects the sodium calcium exchange. This increases intracellular concentrations of calcium, which is available to activate the contractile proteins actin and myosin, thereby enhancing the force of contraction. All right, so an example of one of these positive inotropic agents is Digoxin. Is a purified digitalis preparation from Digitalis lanata and represents the most widely used digitalis glycoside, which is why we had to mention it. So we have our sugar, our glycoside portion here, we have our steroid portion here, and we have our butyrolactone ring here. So as we said, this is the most widely used glycoside. This wide use is primarily a result of its fast onset and short half-life. As we can see, it has 2 hydroxyl groups as well as the glycosidic portion. Position 3 of the steroid is substituted with 3 digitoxose residues that, when removed, provide a genin or a glycone steroid, that is the steroid portion, that is still capable of receptor binding but with altered pharmacokinetics. So the other compound that we want to talk about is Digitalis. It's isolated from the same species, other species of Digitalis, and is a chief active glycoside in the Digitalis leaf. In patients who miss doses, Digitalis is very useful for maintenance therapy because of the longer half-life it provides. So the longer duration and increased half-life are a result of the lack of the hydroxyl. Notice here that we have a hydroxyl here for Digoxin. For Digitalis, we don't have that hydroxyl here. So the longer duration and increased half-life are a result of the lack of C12 hydroxyl that is present in Digoxin. In Digoxin, this hydroxy plays 2 roles. So 1, it serves as a site for metabolism, which reduces the compound's half-life. And 2, it gives more hydrophilic character, which results in greater water solubility and ease in renal elimination, which is why, the half-life is important there. All right, so we have a question. What's the difference between the cardinalides and the bufadienolides? What's the difference structurally? All right, so as we said, the major difference between the two is the fact that at position 17 on the steroid, we have in one case an unsaturated butyrolactone ring, and in the other case we have a alpha pyrone ring. So structurally, that is the major difference between our cardinalides and our bufadienolides. All right, so we have the structures and some names of some other positive inotropic agents. So dopamine, which we know about. We also know about dobutamine, right? And, you know, some others seen here. So these are other positive inotropic agents. And our final question, which I expect you to have the answer in class. Describe the effect of calcium and beta agonists in regulating smooth muscle relaxation contraction. So tell me the effect of calcium and beta agonists in relating smooth muscle relaxation and contraction. So relaxation and contraction. All right, so this is where we end today's lecture. Thank you so much for watching, and see you next time.